Math 2414, Parametric Curves, Video 6, Range Restrictions on the Parameter. What does that mean? Well, first let's take a look at these two parametric equations. X equals sine of theta and y equals sine squared of theta. Although they involve trig functions, we really don't need to find a trig identity that connects the two, because one is just sine and the other one is sine squared. Notice there are no restrictions on the parameter, which I did call theta intentionally this time. Excuse me. But these functions have range restrictions. What does that mean? Well, you all know what the graph of sine looks like. The graph of sine looks like this. It can only go between 1 and -1. Since x is equal to sine of theta, that means our x can only go between 1 and -1. And y is restricted even more, because not only is it sine, it's sine squared. And if you square a number between 1 and -1, you get a number between 0 and 1. Now, you don't really have to think all that. If you're going to sketch this manually, you can just do it. In fact, let's go ahead and try to sketch some points on here. When you sketch points on a parametric curve, and the parametric equations are trigonometric in nature, it's not as easy to come up with values for the parameter that follow a nifty arithmetic sequence. What I would recommend is pick angles that are easy to calculate and get answers to. For example, let's start with, well, normally I'd start with 0, but let's start with negative pi over 2. Sine of negative pi over 2 is -1. And when we square that, we get 1. Remember, y is just the square of sine. It's almost like y is just the square of x. Let's go to next go to negative pi over 3. And the sine of that is negative square root of 3 over 2. And when we square that, we get 3/4. And then we'll move to negative pi over 4. I'm just making all the stops on the unit circle. Why did I start at negative pi over 2? Because I wanted to have some negative values for theta. The sine of negative pi over 4 is negative square root of 2 over 2. And if you don't know where all these values are coming from, you better review your unit circle and your trig definitions. If we square that, we get 2 over 4, which reduces to a half. Negative pi over 6 would be our next convenient angle. The sine of negative pi over 6 is -1/2. And when we square that, we get 1/4. And now we'll go to 0, the sine of which is 0. So when we square that, we also get 0. Let's go ahead and make another table for our positive values. Didn't space it out too well, but I'm not going to reorganize everything right now. We'll just go up to pi over 2, making our convenient stops at pi over 6, pi over 4, pi over 3, then finally pi over 2. Well, our x-coordinates are just going to start being the same ones we had, except in reverse order and positive. So 1/2 square root of 2 over 2, square root of 3 over 2, and then 1. And when we square those, we're going to get the exact same y-coordinates as before. 1/4, 1/2, 3/4, and 1. Notice that the x values go between -1 and 1, and they can't escape that interval because it's sine of theta, and sine's range is -1 and 1, hence the range restriction. Our y-coordinates, however, are only going between 0 and 1 because they're the sine of something squared. So we don't need a whole lot of room to draw this graph. We only need to go between -1 and 1 on the x-axis and between 0 and 1 on the y-axis. When we were at negative pi over 2 for the time, our point was at -1, 1. So we'll put that point there and label it that this is t equals negative pi over 2. Our next point was at negative square root of 3 over 2, 3/4. And for the purposes of graphing, it's pretty handy to know that negative square root of 3 over 2 is about -0.86. And while we're at it, negative square root of 2 over 2 is about 0.70, or 71 if you will. All right, so let's go back to the graph, and our next point is at negative 0.86 comma 3/4. It might help us if we partition things into quarters. Negative 0.86 is about over here, and then up 3/4 we'll put it about here. So this is where t is equal to negative pi over 3. I'm going to pause the video and plot the rest of the points that we have so the video isn't too long. And there's the rest of the graph with all the points labeled with their values of t and the orientation moving left to right. But a couple of comments. Number one, this looks like part of a parabola. Number two, what happens before and after the orientation that we have? Because based on what we see, it looks like the parabola just swoops in from here and would continue going upward that way. But does it? And the answer is no, because this is based on the range restrictions. Specifically, our x's, which are equal to sine of theta, can't leave between -1 and 1. And our y's, which is sine squared theta, can't leave between 0 and 1. And it looks like we've covered that whole spectrum. But what would happen if the parameter kept increasing? For example, what would happen if we went beyond t equals pi over 2? Well, without getting more points out, what would happen is when it hits the top of here, it would turn around and start going back the other way. And in an upcoming video, I'm going to illustrate how this works. And then it would turn around and come back around. So it's almost like you got this little ball going back and forth, destined to stay there forever. So it looks like part of a parabola, but to confirm that, we should probably eliminate the parameter. As we mentioned, these have trig functions, but we don't need a trig identity because we can use the third technique for eliminating the parameter that we came up with. Instead of solving for t, solve for an expression of t that is contained in the other equation. So what does that mean here? That means since sine theta is common to both equations, we can solve one of them for sine theta and substitute into the other. Now, clearly, x is the first equation is already solved for sine theta. And this is basically saying everywhere we see sine theta, we can replace it with an x. So instead of sine squared theta, we get x squared. So the parametric equation in rectangular form is y equals x squared, which of course is the standard parabola. But it's not all of it in this case because the range restrictions on the parameter force this parabola to stay between -1 and 1 on the x-axis, which also forces it to stay between 0 and 1 on the y-axis.